In this lesson, we are going to look at thunderstorms, concentrating mainly on their formation and the potential hazards they pose to pilots. Well-developed cumulonimbus clouds are required for thunderstorms. Wind shear is a similar phenomenon, but far more severe. It is not rough air as such, but airflow that has marked variations in speed and/or direction. Wind shear differs from turbulence in that it will displace the aircraft abruptly from its intended path, such that substantial control action is required to maintain heading and speed. An unstable atmosphere, in other words, an environmental lapse rate greater than the saturated adiabatic lapse rate, and this must extend to well above the freezing level. Sufficient water vapour to form and maintain the cloud, and a trigger action to produce the initial ascent of the air. There are several trigger mechanisms which will cause air to ascend and begin vigorous convective activity. The first of these is through convection from surface heating. Because the surface of the Earth heats up unequally, air lying adjacent to warmer surfaces will become less dense than air above colder surfaces, and this less dense air will rise. Air can also be triggered to rise by being forced up the sides of mountains and hills. This is called orographic uplift. If two air masses were to move together, air will again be forced to rise. This type of trigger action is known as convergence. Lastly, air will rise due to frontal uplift. This occurs when warmer, less dense air is forced up and over colder, heavier air. There are generally two different types of thunderstorms: those that occur in a single air mass, most common in summer, and frontal thunderstorms, which are the more common type in winter. In non-winter months, thunderstorms can be caused by convection, convergence, or orographic uplift. This air mass or heat-type thunderstorm is most frequent over land and generally forms by day. Although mainly isolated, this type of thunderstorm does on occasions form in organized lines or large groups, which we shall discuss later. Thunderstorms also occur on cold fronts or very occasionally on occlusions. They are often embedded in layered cloud, which makes them particularly hazardous to aviation. This type of thunderstorm forms mainly over the land and is more common in winter months. The next issue we must consider is how air mass thunderstorms develop. There are three main stages involved: the initial stage or cumulus stage, the mature stage, and finally the dissipating stage. Let us examine each in turn. The initial stage is characterized by strong updrafts and by the rapid growth both horizontally and vertically of cumulus clouds. Strong updrafts produce clouds of great vertical extent. Air is drawn into the cloud from beneath and from the sides. This stage usually lasts for around 20 minutes and produces a cloud sometimes 5 nautical miles across and 25,000 feet high. The mature stage is characterized by strong up and down drafts and precipitation. Rain, hail or snow can be produced, and as these fall, strong downdrafts occur. Downdrafts can reach 2,000 feet per minute, bringing cold, heavy air down to lower levels within and below the cloud. These downdrafts are frequently colder than the surrounding air beneath the cloud, causing the air to sink at a faster rate and present a major hazard to aircraft caught beneath the cloud. The up currents within the cloud can reach 10,000 feet per minute, and the cloud top may grow upwards by as much as 5,000 feet per minute. At this stage, the cumulonimbus will begin to develop the characteristic fibrous anvil top. The rising and falling water droplets, hail and snow, produce a build-up of static electricity. The top of the cloud becomes positively charged and the lower part negatively charged. The build-up eventually leads to lightning discharge and the characteristic boom of explosively heated air, which is thunder. Microburst and gust fronts are other features of the mature stage. Microbursts are created by the cold downflow of air beneath the cloud spreading out when it reaches the surface. These are very dangerous. The rate of sink of the air sometimes exceeds the climb performance of some types of aircraft, thereby forcing them to the ground. A good visual clue to pilots is the presence of virga. This is precipitation which is falling but not reaching the ground and looks like tendrils hanging beneath the cloud, as shown here. The leading edge of this outflowing colder air beneath the storm is known as a gust front. It marks a rapid change in wind direction and speed, with a noticeable temperature drop. Gust fronts can be made visible as the colder air undercuts the warm air, forcing it to rise and creating a cloud. These are known as roll clouds. The dissipating stage of a cumulonimbus starts as the anvil top becomes fully formed. This stage is characterized predominantly by downdrafts. However, updrafts can still prevail at the top of the storm, feeding the growing anvil. Precipitation at this stage is usually heavy. Lightning and thunder are also still likely at this stage, which may last for between 1.5 and 2.5 hours. Once developed, these types of storms move in the same direction as the winds at around 10,000 feet. The individual thunderstorms, although on occasions quite large, do not last any longer because the downdrafts caused by the precipitation suppress the upcurrents necessary to maintain the cloud. The two effects therefore cancel each other out. The storm effectively dies once precipitation commences. The next section in this lesson will concentrate on the hazards which thunderstorms pose to pilots. Select each named hazard on the screen to learn more about it. When you have viewed them all, click the Forward button. Severe turbulence can occur in and around any cumulonimbus clouds, and particularly around thunderstorms. The violent up and down drafts within the cloud are especially hazardous. The downdrafts and associated wind shear are particularly dangerous during takeoff and landing, since the aircraft is in a configuration of high drag and low forward speed. Wind shear can result in a loss of control, as well as reducing airspeed to stalling speed. Structural damage from turbulence can occur to airframes, and in severe cases lead to terminal failures of the wing fillet. Severe icing may occur in cumulonimbus or thunderstorm cloud between 0 and -45 degrees Celsius, but can be particularly significant in the range -3 to -10 degrees Celsius. High concentrations of large supercooled water droplets can lead to severe clear icing on the airframe very quickly indeed. To avoid this, do not fly into the cloud above the freezing level. Carburetor or engine icing can occur at temperatures between -10 and +30 degrees Celsius in the high humidity associated with any cloud. Hail can be encountered at any height in and underneath a thunderstorm. Even within a few miles of the storm itself, you must expect hail. Hail can also be experienced beneath the anvil outside the cloud. Severe damage can be caused to the skin of the airframe. Any damage to an aircraft will significantly reduce its performance, particularly if the damage is to the leading edge of the wing. Lightning is most likely to occur 5,000 feet either side of the freezing level in a part of the cloud that usually has a temperature between +20 and -10 degrees Celsius. Lightning within the vicinity of an aircraft can cause the following effects: temporary blindness, erroneous compass reading, the ADF becoming unreliable, often pointing into the storm itself, skin damage if the aircraft is struck by lightning, ignition of the fuel vapor if the fuel tanks are nearly empty. Large pressure variations can occur in and around cumulonimbus and thunderstorms. Rapid pressure fluctuations can lead to errors in indicated height of up to ±1,000 feet. Inaccurate height indications and severe downdrafts are potentially very dangerous conditions. If the altimeter is fluctuating, don't fight it. You could overstress the aircraft. It is more important to maintain attitude rather than altitude inside the storm. Aviation authorities have produced guidelines on avoidance distances using radar-equipped aircraft. Here is a table showing recommended distances from cumulonimbus activity. Most private pilot flights will take place well below flight level 200, and no radar equipment will be carried. Therefore, light aircraft should avoid thunderstorms by at least 10 nautical miles horizontally and 5,000 feet vertically. Thorough pre-flight planning is particularly crucial in weather where strong convection is expected. Low-level significant weather charts as well as TAFs should give a good indication for timings and location of cumulonimbus or thunderstorm development. If this lesson has achieved its objective, you will now understand more about thunderstorms, how they are generated, and more importantly, how to recognize and avoid them. They are very dangerous, and it is a frightening experience to be caught in one. Treat them with caution, and before you fly, analyze weather reports and forecasts, carefully looking especially for any signs of thunderstorm activity.